Hello, Math 8 students. This is Open Up Resources, Unit 2, Lesson 6 on Similarity. To get started, we've got this interesting warm-up, and I'm not going to spend a ton of time on it because I really want to focus on the bulk of the lesson. But this is a really good review of last year's learning, which I know most of you skipped because it was springtime. I will find out now who watched the videos and who didn't, which is going to be probably most of you didn't. But I already know that going into it. It does say, use what you know about operations and their properties to write 3 expressions equivalent to the expression shown. Pause the video, give yourself a chance to do that, but please don't spend more than 60 seconds because I bet you're probably going to do it wrong. And I don't want you to spend a lot of time doing it wrong. I just want to be able to show you the right way. But I do want there to be some thinking. So 60 seconds, go. Okay. What this says is we need to use what we know about operations and their properties. It doesn't say simplify or evaluate the expression. This is probably what you did, but this is also not what it's asking to do. To simplify the expression, we would use our order of operations, which is gemma, grouping symbols first, then exponents, which there aren't any, then multiplication and division, and then finally addition and subtraction. But we do have grouping symbols right here. Our parentheses, 2 plus 3, we would simplify, and that is 5. Now again, this is not what the instructions are asking, but this is what most of you did. So we're going to talk about what you did. We would have to do our multiplication next. 10 times 5 is 50, minus the 8 times 3, which is 24. And finally, we get to 50 minus 24, which is equal to 26. Raise your hand if that's what you did. Good, you did the expression correctly, but not what it says to do. So let's talk about what it actually says. Use operations and their properties. So I'm going to be doing a little bit of color coding. I'm going to rewrite the expression each time, color coding only the bits and pieces to change. And I'm going to get started with the commutative property of addition. And this is the stuff that we should have been looking at. Commutative property of addition. Because again, it says using operations like addition, multiplication, and their properties. And the commutative property of addition tells me it's okay to change the order of addition. So in this expression, I have 2 plus 3. I can change that to be 3 plus 2. I'm not making any other change, but I am rewriting the expression to be an equivalent expression shown. Do you understand the directions now? And this is how I know that most of you probably didn't do this correctly because this was all done during the spring. And I know that that was interrupted learning. Let's take a look at another one. Another one that we could have written is the commutative property of multiplication, where I can change the order of multiplication. So again, writing the original, 10 times the 2 plus 3 minus, if I wanted to, I could change the order of this multiplication. Instead of 8 times 3, I can do 3 times 8. Just 2 more that I'm going to go over. There are lots of ones that we could have done. The next one is inverse property. Of addition. And that looks like this. This is one that I talked about a lot, not just in the spring. That when I see subtraction, I can change that subtraction to adding a negative. And the last one to talk about is distributive property. Does anybody remember from the videos last spring what the distributive property is? Exactly. Landis, you were pretty confident that you did these correct. Have you gotten any of them? Okay, distributive property would look like this. I'm going to come back to the original. I'm going to rewrite 10 times the quantity 2 plus 3 minus 8 times 3. This is our original. And the distributive property is just like making a peanut butter and jelly sandwich. Let me explain what I mean. This is the peanut butter right here. See it? These are your 2 slices of bread. The best, most correct way to make a peanut butter and jelly sandwich is to put the peanut butter on this slice of bread and to put the peanut butter on this slice of bread. If you don't, if you only put it on one slice of bread, when you put the jelly on, what happens to your bread? It gets soggy. And so when we make peanut butter and jelly sandwiches, it's best if we put peanut butter on both slices of bread. We're distributing the peanut butter to this bread and distributing the peanut butter to this bread. So what that really means is we're not just multiplying the 10 and 2, we're multiplying the 10 and 2 and the 10 and the 3. So the distributive property tells us it's 10 times 2 and 10 times 3. And then we could do the minus 8 times 3. So let's back up and see. If I did it the way the order of operations tells me that I need to do the parentheses first, I first would have added 2 plus 3, and I get 5. Then I would multiply, and 5 times 10 is 50. But if I do it this way, I have 10 times 2, which is 20, 10 times 3, which is 30, and 20 plus 30 is 50. So we get the exact same thing. The distributive property is a great way for us to kind of go in a little bit different order and still get the correct answer. So remember, distributive property, think of your peanut butter and jelly sandwich. And now, with that in mind, we're going to move on to the bulk of our lesson. To really understand what we're going to be talking about today, we do need to review dilations. Remember that dilations are a transformation that produce scaled copies. In dilations, angle measures are preserved. That means that they stay the same. Side lengths, however, are scaled up or down. So since the side lengths are changing, that means that we are making non-congruent figures. Dilations do require a center of dilation, and they require a scale factor. That was something that we observed in our last video and our last lesson. We're going to talk a little bit about similarity. That's what this whole lesson is talking about, is similarity. To get started, I know that you have heard the word similar in a real-world context. So I want you to take a few seconds and write down. We're not talking at this point, we're just writing down. How have you heard or used the word similar in a real-world setting? What does it describe? All right, you've had a chance to write down what you know or what you think similar means in a real-world setting. Looking for just a few comments. Zeta? Okay, not the same, but close to the same. Any other comments? Emily? Okay, good. It's a comparison word. Other thoughts? I need at least one more student. Cole, I saw that your hand was raised. Not what we're talking about, Landis. Say that again. They look alike? Okay, good enough. Similar in mathematics is very similar to similarity in the real world, but it's got a really precise definition. We're going to write that precise definition now. And this precise definition is going to feel somewhat familiar. So similar in mathematics, make sure you're writing this down with me. It means two figures are similar if one can be obtained from the other lots of writing here through a sequence S-E-Q-U-E-N-C. Does this feel familiar? Have we said another definition very similar to this? Two figures are, I said a different word, if one can be obtained from the other through a sequence of, yeah, I heard it. Someone said rigid transformations. That's how we've always finished this before, right? Only we're not finishing it that way this time. It's similar, but different to that definition. Two figures are similar if one can be obtained from the other through a sequence of translations, rotations, reflections. I want to pause and make sure that we understand that this translations, rotations, reflections, those are the rigid transformations. So in the past, we would always say through a sequence of rigid transformations, meaning translations, rotations, reflections, but now we've got something else. Our new transformation is dilations. So I'm not saying rigid transformations anymore. I'm listing the specific transformations and including a new one. And dilations. That's really the only difference between similarity and our last definition that was similar to this, which is congruence. Okay, so really, truly, this is a really familiar concept. The difference is now we're allowed to do dilations. And when figures can be related through dilations and some of these other transformations, we use this word similar. So let's tie this in. Dilations produce scaled copies. So the difference now is that when we are allowed to do dilations, that means that similar figures are scaled copies. To prove that two figures are similar, all we need to do is describe a sequence of these transformations to show that one will line up on the other. So this first one we're going to do together. I want us to talk about it together. We're going to write down the different pieces of information because on the very next page, that's when you're going to be working on these ones on your own. So we're practicing together now. Use this example, make sure you're writing everything down. So I've got this figure, and I'm trying to show that it's similar to this figure. So in order to show that, I have to do a certain sequence of transformations. The first thing that I'm going to do is I want to translate D to H. So I'm going to write that down. I'm going to translate. How far am I translating? It looks like I'm going right 1 and up 2. Translate A, B, C, D, 1 unit right. And 2 units up. So again, this is a lot of the same stuff that we did all of last unit. I make this first transformation. Well, what I need to do next? Can anyone visualize it? Landis? I am going to have to rotate it. So let's be really precise. I would have to rotate, and we're wanting all that same precision from the last unit to be what we use here. I'm probably going to use this as my center of rotation. I'll do that one in green though. So I'm going to use H as the center of rotation, using H as center. Rotate. How much am I going to be rotating? 90 degrees. Which direction? Clockwise. And again, forgive that I don't have this geometry software. I'm going to rotate that, and then I'll have to get it back into place. Okay, is it going to line up perfectly yet? What else do I have to do? Can you guys see? I know we have to dilate, but there's something that has to happen before that. Callista? We do have to flip it, which means that I would be doing a reflection. And what line should I be reflecting it over? We don't have an x-axis or a y-axis, but I can draw a line that would go through these points, right? I don't know why it randomly changed to black right there. So now we would need to reflect over line HF is what I'm going to call it. I'm calling it HF because it goes from H to F. So I'm going to do that now. Flip up, down. Now I have to get it back into place. Now it's looking really close, right? One last thing. What is it? The last thing that I got to do? Nadia? Dilate. And we want all the details of our dilation as well. So we know that we're going to dilate. What is the center of dilation going to be? H is the center. Good. And it's really nice when you can make some of these points in the figure already line up. It helps you identify that center. For example, H is already where that other point is going to be. And if I look, I can see this vertex here corresponds with this vertex. And look at that. They're all in a line going back to H. Same thing here. These ones correspond. They're all in a line that goes back to H. And these ones are all in a line going back to H, which tells us that H is the center. But when we have dilations, we also need to include the information about the scale factor. So what is the scale factor? I'll help you out with this one. The rest of them you're on your own. Cole, you already know? It is 2. Here's some things to check. Notice we're going from the center to this point. And what is that distance? 3. But what is that distance to the corresponding point? Here's the original, or here's the center, going all the way out to where that point goes to, and we can see that that is a distance of 6. So how does a 3 change to a 6? We multiply it by 2, therefore the scale factor is 2. Other ways that you could check that, we go up 1 and across 4, but to get to the dilated part, we have to go up 2 and across 8 because we're multiplying by 2. So that's another way that we can check. And that's it. That's it for my instruction. Now it's your job. I want you to work with your groups, and I want you to do the exact same thing for these two figures. Show a sequence of translations, rotations, reflections, and dilations that will take one figure to the other. If you can do that, then it proves that they are similar. Just to keep everything consistent, let's start with our small triangle here, transform it so that it can become the big one, and similarly, let's start with the small one and transform it so it can become the big one. I want you to work with your groups, online learners, pause the video, do this on your own, and return to check your answers. Okay, get me started, please. What is the first move I need to make to move this triangle so it matches up here? Let's start with Zeta. Perfect. Up 3 units, left 2 units. Now, I already know, because I walked around the room, that a lot of students didn't translate the triangle to here. They translated it to here. Guess what? That's okay. It just means that your sequence of transformations is going to be a little bit different. But as long as you can define a sequence, then you're good to go. So let's follow along with this one. Translating it here to this position, what would our dilation center need to be? Cole? It would have to be E here. If you translated it over to here, what would your dilation center need to be? Lucas? G. Good. No matter what our center of dilation is, what is the scale factor? Nadia? 2, exactly. And we can check that out by seeing that this is 2, and the whole piece of that new triangle is 4. How does a 2 change to a 4? Times 2. So dilate using center E and scale factor 2. Easy peasy, right? Okay, next one. I know you may not have had quite enough time to finish this with your groups. Get me started. What's one of the first things that I could do here? I'm seeing the same hands. Any new hands? All right, Nadia. We do have to do a reflection. That's the first. And my last class, they wanted to translate it first, and that's okay too. But since you see a reflection, let's reflect it. Which line should I reflect it over? Landis, what would you reflect it over? Yes, if we were starting with the big one. I'm going to start with the little one, so I think there's a little bit easier way to describe it. Again, not wrong. It just means that your translation might look a little bit different. So reflect A, B, C, D, E, F over. Nadia, what line would you reflect it over? I like D, E. And that will put it right here. Oh, it's so close to lining up, isn't it? Looks like it needs just a tiny, tiny, well, I guess a bigger translation because we need to move it all the way over here. So here's what I would do next. We're going to have to call a point. I'll just call that one B because it was, no, I lied to you. This one is B. Or we can call it B prime since it has been moved. But now what I have to do is I need B prime to line up with G. And I can't describe how that is. I don't know if it's 1 unit left or whatever, but I'm just going to describe and say translate. So B prime goes to G. And now I know exactly what that's supposed to be, no matter how you did your reflection to begin with. Maybe you reflected it over a different line, but now I just know that the translation has to get that B prime over to G. And then when I do that, now it looks like this. What would the center of dilation be now? Can you see it? Landis? No? Cole? It would be G. Eyes on the screen. Take a look at this. Do you see how G and B prime already line up? That's a good sign. That's probably the center. Here's ways that we can check. We can get our ruler out and see this vertex. Does it line up with the corresponding one? Yep, and it goes back to the center. What about this one? Yep, they line up and go back to the center. What about these ones here going straight down? Yep. So have we found our center? Yeah, because everything goes back to that point G. Oops. Doesn't like this because this went all the way off the screen and it's freaking out. And even if I Control Z, it won't get rid of it. And deleting it doesn't get rid of it. So you guys are good with just leaving that there, right? Okay, good. So we would translate so B prime goes to G, and then we would need to dilate. Oh, so that happened. There we go. Dilate. Using G as the center. Scale factor is harder because, again, we don't have anything to measure. We don't have grid to count. But we can use our little index cards. And if I use my little index card, I would see, do you see this side length right here? How many of those, oh, make up here? There's one. Trying to be fast, and in trying to be fast, I'm being a little bit slow. There's one, there's two, and there's three. So what would that scale factor be? 3, yep. Now, what if when I translated it so that it lined up right here? What would the center of dilation be? I. What if I translated it so that these ones lined up? Scale factor is J, exactly. So identifying that scale factor doesn't have to be hard, especially when you have points that already line up together. And now we've got this lovely Are You Ready for More, which I really do love, but I'm going to go through it quickly. Instead of having you guys think through this, I'm just going to walk you through it. Because it really does take a lot of thinking, but there's a homework problem similar. So I just want to make sure we have time to understand this problem, therefore our homework problem. It says the same sequences of transformations take triangle A to triangle B, and then it takes triangle B to triangle C, and then triangle C to triangle D. So just real quick, what are some things that are happening? Are we seeing reflections, translations, rotations, dilations? What is it that you're seeing? Lucas? Yep, I see a rotation. What else? Parker? Actually, I'm not seeing a translation. If we just do a rotation, we can take care of it. Cole? A dilation. Good. So let's talk about those two things independently. What I first want you to do is recognize, do you see this 90 degrees right here? And do you see how this 90 degrees is split up into 1, 2, 3, 4, 5, 6 pieces? So what is 90 degrees split into 6 pieces? What is each one of those going to be? 90 degrees split into 6 pieces. I see calculators moving. Yeah, did you do that in your head? Good job. 90 divided by 6 is equal to 15 degrees. So each one of these little pieces is 15 degrees, okay? That's going to be helpful to note first. The next thing is, do you see how this part of A rotated down to be this part of B? Okay. So then, what is that angle? Knowing that each one of these are 15, count it out. 15, 30, close. 45, 60. I'll try that again. It is 75. 15. 15 more is 30. 15 more is 45. 15 more is 60. And 15 more is 75 degrees. So we are rotating 75 degrees clockwise around the center. Here's the next thing to observe. So please make sure your eyes are on the screen. You mentioned that it's a dilation. And this is kind of, there's an easy way to figure out the scale factor of this dilation. And that is to measure, always to measure the distance from that center of dilation. So look at our original triangle. Do you see how this point here is on the first radius, giving it a distance of 1? But in the new figure, It's no longer on the first radius because it's on the second. So that gives us a distance of 2. How does a 1 change to a 2? Times by 2. So this is a dilation with scale factor 2. And I didn't name the center because the center of dilation is the center. And center as the center. Okay. Ready to move on? Feels like a race, right? We're going through this so fast. Here, these are just sketches, so we're going to get through this also super fast. I'll help you through the first couple. We're sketching figures that are similar to A. Now it says sketch. Now when it says sketch, it's okay for it to be a little bit imperfect because it's a sketch. Even though it's going to be a little bit imperfect, we want it to be close enough that we can tell that they are similar. So in this first one, it says a translation and a reflection. So if I take this figure and I translate it, and then I reflect it, have I produced a similar figure? Yeah, because I've done a reflection, which is good. I've done a translation, which is good. I'm going to label that B. So when you do this on your own, you would sketch something that looks like that. Perhaps you reflected it down, perhaps you reflected it a different way. But we can do a reflection and a translation, and your sketch should look relatively the same. Yeah, sort of. It's a sketch, but we should be able to tell that it's an attempt to make them look the same. Now turn your attention to me real quick. I know online learners, you can't see a video right now, but I want you guys to observe. Do you see how figure A kind of looks like a hand? It's like a thumb. This little short side here is like a thumb. And then this is like your hand, your fingers. They're a little bit longer. So can you mimic that with your own hands? That would be a reflection and a translation, right? You're just kind of flipping it. Okay. Now, let's do part 2. A reflection and a dilation with scale factor greater than 1. Let's just talk for a second. If I have scale factor greater than 1, what's going to be happening with this figure? Bigger or smaller, Zeta? It's going to get bigger. Does it say how much bigger it's going to be? No, it just needs to be bigger. So I'm going to make it bigger. And then I'm going to reflect it. I'm going to go up, down this time. And it says label that one C. Again, make your sketch. It just needs to look relatively the same. Sketches aren't going to be perfect, but we want it to keep the same basic shape. Perfect? Perfect for a sketch. Okay. And this is the last one that I'm going to make you do. We're going to skip down to number 4. A dilation with scale factor less than 1. A scale factor less than 1 is going to make it be smaller. And again, it doesn't say how much smaller. Even just a little bit smaller is still a scale factor less than 1. And it says a translation. So here's what I'm going to do. Translating it just a tiny bit. Scale factor nice and small. That one's labeled D. And I'm sorry that was rushed, but now we're ready for our summary. Let's show that triangle ABC is similar to triangle DEF. To do that, we need to remember that two figures are similar if one figure can be transformed into the other by a sequence of, not rigid transformations, but translations, rotations, reflections, and dilations. There are many correct sequences of transformations, but we only need to describe one to show that the figures are similar. So maybe you describe a different one than your partner, that's okay. As long as you can describe one, that's what matters. Here's how they did it. One way to get from ABC to DEF is to follow these steps. You can reflect across line F. Notice, in the original diagram, line F wasn't there, but they added it. So we can reflect across F. Then we would rotate 90 degrees counterclockwise around point D. And that gets us to this position. And then we would dilate using scale factor 2 so that B ends up going to E. Another way you could do it is described here, but we're going to move on. It's time for your cool down. Elena gives the following sequence of transformations to show that these figures are similar. She's trying to transform ABCD into EFG, and she says, dilate using center D and scale factor 2. Then reflect using line AE. Work with your groups to identify, is Elena's method correct? If not, explain how you could fix it. Work with your groups. You have about 30 to 60 seconds now. Ready, set, go. All right, let's take a vote. Is Elena's method correct? Is it going to work? Why? Why isn't it going to work? Parker. Well, that's what she says, using line AE. So let's try and do what she says. She says dilate using center D and scale factor 2. So I'm going to do that. Come on, technology. Looks like I need to go a little bit more. All right, that's what the dilation would look like. Looks good so far, doesn't it? Now let's reflect over line E like she says. And reflecting over line E is going to put it up here. Is that going to really work? No, we do need to reflect it, but how should we have reflected it? What line should we be using? Nadia? Yeah, and there isn't a line there, so what I would say is I would either draw that line or describe it and say the vertical line that goes through D. I'm even going to call that line L, using line L. And I can use line L because I drew it and I labeled it. Your homework are the lesson 6 practice problems. Online learners, don't forget to enter your cool down answer in Canvas and complete your homework in Canvas. That's it for today. Thanks for watching. We'll see you next time.